Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Boren Gu, who will tell us about QGPU, parallel logic in quantum LDPC codes. So Boren is a PhD researcher in quantum error correction and fault-tolerant quantum computation, and he's supervised by Jens Heise at the Free University of Berlin. His research is focused mainly on quantum LDPC codes, logical gate implementations, and architectures for scalable fault-tolerant quantum computing. And he himself is particularly interested in finite-size quantum codes with good parameters and logical operations to enable efficient logical measurements and high parallelism computation. So, Boren, the floor is yours.
Yeah, thank you very much for the invitation. And yeah, so as we have already discussed a bit with Jello, that I'm mostly interested in the finite regime of quantum low-density parity-check codes or quantum error correction. So that may be slightly different with what most of you are doing in a really asymptotic regime. So bear with me if I show some code parameters that starting with like 100 of physical qubits also. Yeah, so today I'm gonna just like talk about a recent work where we have this kind of QGPU thing, but this is just like for a ideal illustration. It is not a real GPU in quantum sense. It is not. We're not dealing with the graphs either. We're just like try to emphasize on the parallelism of logical operations that we can do with a specific code and logic co-design. Yes, so first let me introduce my collaborators very fast, like what's best collaborators ever. And Andy from Yale, Amanda from FU Berlin, Qian Xu from Caltech, Jens Heise, my current supervisor from FU Berlin, Yosh Garov from University of Edinburgh, my previous supervisor. Okay, so let's speak of the high-rate quantum low-density parity-check codes. So we know things like almost like around 5 to 10 years ago that we have this kind of quantum high-rate low-density parity-check codes. They're good in quantum memory, for example, like hypergraph product codes, bicycle bivariate codes, lifted product codes. So they are high rate compared with the surface code, which is also LDPC, but they always encode one logical qubit in a certain patch. And so maybe you are familiar with the lifted product code as the first asymptotically good quantum low-density parity-check code. But the problem with this is, are they really good at logic? So we know that surface codes, which we can easily perform logical operations via, for example, so-called lattice surgery, or even do the logical operations transversally. But when it comes to the high-rate quantum LDPC codes, things are slightly different, or like they're even very different. In terms of, for example, like we consider a high-rate code, there are many logical qubits encoded in one code patch. And there are very often the case that many logical operators, they heavily overlap with each other. So each, like the color regime is a supporter of a logical operator, and they overlap really much. And it is really hard to get single logical addressability without triggering other logical operators, at least part of them, like simultaneously. So it is quite hard to, like say, realize parallel logical operation or measurement, something like that. Or at least you will need extra physical overhead to get your logical operators preserved. In that sense, such kind of like high rate is taking some trade-offs, because like you are high rate in space sense, but on the time scale, it is not high rate anymore. So this work is kind of like to deal with this problem in a sense that we propose a code which is called the clustered-cyclic, which ensures CC code. And we also introduce a co-designed way to do the logical operations. It's called the parallel product surgery. And with this kind of like logical code co-design, we are able to realize, so if we have k logical qubits, we are able to realize k over 2 disjoint logical pair measurements in a same surgery round. So I'll explain the terms term by term later on. So this is like, say, very naturally the upper bound that you can get for k logical qubits, because like you just partition them into two pairs. And the reason that we are interested in kind of joint logical measurement is because like we want to do them such that we can perform later on the measurement-based quantum computing in a fault-tolerant way. Yes, so you may feel free to stop me like anytime, or maybe just like afterwards. So for this one, I would like to go through the whole talk in the following sense. We first introduce the CC codes and some crucial property of this CC code. And later on, we just introduce this kind of like surgery. So we start with a very tiny example of lattice surgery for the surface codes, which you may be familiar with. And later on, we see how to generalize this surgery language into the CSS codes for all CSS codes. And we show that, okay, so particularly if we add some constraints on the auxiliary system that we choose and how we connect the auxiliary system to our codes, we define this kind of product parallel surgery. And we show how we can achieve this maximal number of measurements. And yeah, as a bonus point, we show that for a 24H3 CC code. So for ones who not quite familiar with these code parameters here, 24 is number of physical qubits, often labeled by n, and the number of logical qubits, which is labeled by k, and the code distance labeled by d. So this is a 24H physical qubit encoding 8 logical qubit and has distance 3. Yes, so we show a full Clifford group can be realized with the automorphisms of this code and this kind of parallel product surgery scheme on 4 logical qubits while treating the other 4 as auxiliaries. Yes, so leaf-to protocols. As mentioned earlier, that this is the first family of codes which achieves a almost linear in a symptotic region, and they are a family of the CSS codes. So where you can separate the X and the stabilizer generators, and correspondingly, the logical operators can be separated with only X or only Z type of Paulis as well. And so they are defined as a tensor product of 2 classical codes. So classical codes are just like matrices, but over a ring, which here we consider the polynomial ring quotienting out. So quotient polynomial ring. So in general, it will be some F2 group algebra, something like this. And so for here, for simplicity, we consider the simplest one, the polynomial quotient ring, where the group that you take is just simply a cyclic group. So in this way, we got 2 different representations, but they are equivalent to each other. The first one is that if you represent the classical codes in terms of length 1 chain complex, so it's a mapping, and you take the product of the 2 length 1 chain complex to get a length 2 chain complex, which is simply so these 2 are equivalent, and this is just like a decomposition. So in this sense, you get a what so-called like say length to chain complex representation of a CSS code, also of this product, lifted product code. And on the other side, we have those kind of like very standard binary matrix, very standard parity check matrix representation. But yes, and when we come to a very special case, when this R, the ring is defined over the binary field, then this lifted product code construction defines a hypergraph product code. In short, HGP, maybe you are familiar with. And the service code is a special case of the HGP code. So in short, like the service code is also a special case of this lifted products. And what is important to be noticed is that, as you may be aware, that all our matrices, HA and HB, and also this identity matrix, they are defined over this ring. So you may ask the question, because like we are familiar with the binary parity check matrices. So how do we get the binary version which can be really used? The way to do this is kind of like take the so-called binary representation, which is for every element inside the ring. For example, we consider X to a L by L matrix, and for example, the X is shifted by 1, so it's mapped to a permutation matrix, something like this, and such a way that you get a way to map all, like say, both parity check matrices over the ring onto a parity check matrices over the binary field, but with a larger size. Okay, from a telegraph point of view, this will be simply, you consider, so the color dots are the quantum regime, and the classical ones are the black and white ones. So in this sense, what we are actually doing is that this is a case where L equals to 5. So for each ring element, you consider them as a cluster. So here a cluster is just like a tower of elements, and yes, and after you take this binary representation, you are just like lifting it from one cluster, and you decompose it into 5 or L different physical elements. So here one cluster is 5 physical data qubits, and here 5, like one cluster, it represents 5 check physical qubits. Yes, and you can see like in this chain complex diagram that we have such a correspondence, because like we have 2 kinds of parity check matrix, HX and HZ. Then we are very okay to say, okay, these 2 modules or vector spaces are corresponding to the check qubits. So we are able to lay out the 2 sector of the check qubits. And for the physical qubits, as we can see, it can be decomposed into 2 different R modules or vector spaces. On a telegraph point of view, we are also able to decompose them into 2 sectors. And this kind of telegraph is quite important. So we will use it like to explain the properties of our new codes later on. So maybe you want to keep it in mind. Okay, so as introduced, the cluster-cyclic codes are a subset of the lifted product codes. But in which sense? So this is a general standard parity check matrix for the lifted product codes, but we have some constraints over the seed matrices that we choose, the classical ones, if you still remember. So, and of course, some other constraints. First of all, is when we pick this ring, we no longer able to choose arbitrary L, but instead we want this lift parameter we call to be a odd prime number, and we want the parity-check matrices to be square matrices, the seed codes to be square matrices, and their entries to be either binomial or zero, cyclic suppose of non-zero terms, and some other constraints that listed here. Okay, so this may be very confusing because like it's abstract, but okay, let me show you like two tiny examples. So here we consider a lift parameter to be 5, which is an odd prime number. Very good. And for each entry, it can be either 0 or a binomial. So as mentioned, this ring is a polynomial ring, so we definitely have some binomials. And what we want is that we want the support of these non-zero terms to be in a cyclic way. So as you can see, 1, 2, 3, 4, 5, 6. It is just as if it's a cyclic matrix, replace all the binomials by 1. And so this is a kind of like identity map, like identity, but it is in some sense still a cyclic matrix. So what? So you can just like control the size of the matrix as large as you wish, and yes, but you will need to be aware that we want in the very end the whole matrix is full rank over the ring. Yeah, and okay, that's pretty much the constraint of the seed codes. And owing to the constraint of these seed codes, we're able to read out the logical operators of this quantum code, which is quite crucial. And that's the starting point of this problem that...
Sorry,
Yes.
I wanted to just interrupt. Like, I'm just wondering, like, of course, like, there's probably technical reasons for choosing, making all of these choices, but is there kind of like a intuition as to why you wanted to have this particular properties?
Yes, very nice point. And yes, I'm about to go to that point.
Okay.
So yes, so the reason that we want such a special constraint is that we are the motivation of such a design of such a code is that to have a neat, controllable, or even addressable logical operator basis to get avoid of those very overlapping, messy structures of the other codes. And the way that we do this is with those constraints, and how we calculate those logical operators is the so-called Kunis formula, and it is just a simple way to get the logical operator basis from its classical seed codes for the product codes. So this is a general result for the chain complexes if you get product chain complex. And yeah, as you see, terms and conditions apply. Okay, but okay, yes, it is only true that we can easily derive this when we consider this G to be a finite odd cyclic group. So this is in some sense the reason that previously we choose the lift parameter to be a odd number, but not all the reason why we want them to be odd and prime. But we don't expand on this formula. Yes, okay, so we now come to the question that Jello asked. So why we have those constraints? The reason is, if we have those constraints, then we are able to kind of like restrict the logical operator basis taking such a form, which is that we have a matrix and it is diagonal and chi on the diagonal. So this chi is the so-called full polynomial over this ring, which is you take every entry to be 1 if you consider its binary representation. So it is some matrix like this. So it is like because like you can always represent each monomial by a permutation matrix, and you just sum those monomials together, and as you are summing all the possible monomials, you get a full matrix, a matrix full of ones. And what is nice about this one, or what is nice about the binomial limitations, is that we are able, so there's a very obvious rule that for any monomial taking such a form, like say we get this kind of like chi multiplied by x alpha always equals to chi itself, because like no matter you apply this kind of x to the power of alpha as a shift for this the whole monomial, full monomial, it will always just like rotate or reorder each term, and you still get the same thing. So at the end of days, you get two chi's, and they cancel it out because you are over the field of binary. And in such a sense, you are guaranteed to have such a matrix to be in the kernel of each seed matrix, and then you are able to read out this kind of like each row of this matrix just corresponds to a logical operator of this whole code, of this quantum code. And what does it mean? It means for both types, this is quite important. For both types, they are always they're such a basis that two logical operators of the same logical qubits, they overlap on exactly this chi. And as mentioned, we choose them to be an odd number, so they are overlapping on odd number of physical qubits, so they anti-commute and they are very well defined. But if you look at two logical operators, maybe of the same type, then they are not overlapping at all. So these two cycle of chi's are different p numbers of physical qubits, like i.e. two different cluster of physical qubits. Yeah, so this is a Tanner graph visualization, which will be way easier to understand. So for each cluster, if we consider an operator which overlaps, or like say has support on a whole cluster, at that cluster in the ring level, it's just a chi. So in such a sense, we consider any row here, it will just correspond to a single cluster in this Tanner graph. So for example, we consider this a logical qubit, and whose logical operator of both type are just exactly applying physical z-Paulis on the whole cluster, or x-Paulis on the whole cluster. So that is a very, in some sense, naive addressability, but that brings a lot of convenience. Yes. So we get this kind of a logical operator which resolves the problem of like logical operators overlapping with each other, and you may consider, okay, this seems to be some structure which limits the behavior of the code in total. Because like the reason that we can get some good codes is because that they are making use of, like say, as many as possible the physical qubits in the whole code patch to be a logical operator such that it can maximize their code distance. So it will be a good concern and valid concern that the code distance of this code may not be good. Well, it turns out, reading out from this cluster, we are able to directly get this distance upper bound. So which is the size of each cluster, which is i.e. the Lifter size. So yeah, that is an upper bound. And also we can read out the the number of logical qubits that being encoded in this code. So if you if you start with a seed code with NA and NB as their size, then you are able to read out, okay, the number of logical qubits in this code is just like number of green clusters that we have in this tenor graph, right? So this is easy to show. And however, even though we have this kind of upper bound, we still get some very good code parameters, which is comparable, like in a finite size regime, comparable with the, for example, bicycle bivariate codes or quantum radio codes. So if I zoom in a bit, then you will see this one, the 144.12.12 is a very famous gross code. And we do have something quite similar in parameters and also logical memory simulations if you go to the appendix of our paper. So for example, this 136.8.14 code, or if you want more logical qubits, we have a 198.18.10 version. So the bracket is a leaf parameter, so which is also the upper bound of the code distance. So you will see when the leaf size is quite small, we are able to achieve the upper bound almost like, say, all the cases. But when the upper bound gets like larger, we are less likely to achieve this upper bound, which is very intuitive. And also this kind of fact makes it not a good quantum LDPC code in the asymptotic regime, but we are fine, I believe. Yes, so these are the code parameters. Yes, one thing worth noting is that the CC codes has weight 8. We are listed here. They have weight 8, but BB codes and quantum radio codes, they have stabilizer weight 6. But as we show in the memory simulation, they are just like doing fine as well. Okay. Yes, so owing to this addressability, that we get some very easily understood automorphisms out of this code itself, out of this logical operators basis itself. So automorphism, I would like to explain like in one sentence, which is that we are some physical level operations which preserve the stabilizer group and but have like non-trivial actions on the logical operators. So so I would just like go through the automorphism that we have and you get an intuition. So first of all, that if we want to implement some logical swaps, then what we can do is just simply, we maybe permute some physical qubits intra the cluster. And for example, this one, something like that. And then we may just permute the whole cluster, something like this. And in this way, we get a logical swap because like we have very good addressability of logical qubits. And similarly, we're able to utilize this kind of like ZX duality because this is a CSS code. And for example, like we are able to implement global hardmod gates via, so that is like hardmod on all physical qubits and with some intra and inter cluster swaps or like permutations, then what you get is like logical hardmod on all logical qubits. Similarly for the CAZS gate, that is like we have some intra-cluster swaps and together with the CZ between, so there are representing both logical, okay, so first of all, it's a physical operation. So that is like the second cluster, so which is this cluster, which is this cluster versus this cluster, and you apply the CZ gate one by one in this sense. And the S gates are applied also, just like for each one. And so if you're doing so, what you end up with is a logical CZS, and is displayed in this kind of diagonal graph on the logical level. So this kind of like automorphism groups are, in some sense, kind of like free, and both above two are easily fault tolerant because like they are transversal, and the only 2 qubit gates are the swap, so the error won't propagate. And but for the last one, you may be a bit careful because like you involve some 2 qubit gates, but we showed like in our purpose of having some logical qubits as auxiliaries, we can just like discard those logical qubits and use them as flag qubits in some sense, and to make the thing fault tolerant. Yeah, so these are let's say very cheap, at least, logical operations that you can get. You don't need some extra auxiliaries to make sure the whole process is fault tolerant. But these ones are not enough to generate the full Clifford group. And we now move on to how we do the so-called surgery to realize the Pauli-product measurement and the measurement-based Clifford operations. Okay, so short introduction to the Pauli-product measurement. So Clifford operations can be compiled using the PPMs and with auxiliaries preparing some non-state and up to some polyframe updates, or maybe Clifford updates, but those are not difficult. For example, a CNOT gate, we are able to initialize a auxiliary, and we measure the joint Pauli or the PPM in Z basis and X basis, and then measure out this auxiliary in Z basis, and we do some Pauli correction on the data qubits. Then we are able to do this CNOT. So this is like true on both physical and logical level. But if you want to do this fault tolerantly, what you need to make sure is you want, of course, you will need a fault tolerant logical auxiliary, and you want a logical Pauli measurement, product Pauli measurement, which is fault tolerant as well. Another PPM which is fault tolerant, and a PPM. Sorry, well, this is a Pauli measurement on the auxiliary, which is also fault tolerant. And all those kind of like purposes can be realized with a single product, single process, which we call the code surgery. And the lattice surgery is the first candidate of all this kind of like code surgery protocols for the surface code. So a quick recap. A surface code can be represented as follows, and the dots are the physical qubits where we have X and Z type of stabilizers where are located as shown. And the logical operators of different type are just like on the horizontal boundary or vertical boundaries. So we are displaying two different patch of surface codes. The purpose for this one is to measure the joint Pauli product of X1 logical and X2 logical. So how we do this? We do this in a very simple way. We just initialize two extra physical qubits in the middle as the auxiliary system. And we do some extra checks on the boundaries, so in both types. And there will be some, so you see like we have new Z stabilizer and new X stabilizer. And if the results of the new X stabilizer measurement will end up to be, sorry, this is, let me just clear this up. So the results of the 3 new X stabilizer measurement, as you can see, like they cancel on the auxiliary physical qubits. And the thing that you are really measuring are 1, 2, 3, 4, 5, 6, which are 2 boundaries of the original patch. And as you're considering their product, then you get the product of 2 logical operators. And however, what is important is the stabilizer you are measuring is still at the weight of the original ones, and for this specific case, it's just like you're getting a larger surface code. So everything you're measuring is very legal, and as it becomes just like a larger patch of surface code, the code distance is always preserved, and this whole process is very fault tolerant. Yes, so that's a standard example how you measure the logical operators or PPMs that you want by, let's say, entangling the 2 original logicals or the targeted logicals into a larger system and measure the stabilizers of the larger system. Because like you don't want to measure the logical operators themselves directly, right? Because like after you measure them out, they are no longer quantum. Yes. Okay. So let's turn into a more general language, which is also more abstract and mathematical. In general, like we can represent the surgery process for all CSS codes in the following. So if you remember, this is a CSS code in terms of length-to-chain complex, and we call it a data code. And we put an auxiliary system, which can also be represented as a length-to-chain complex. However, they are not necessarily a valid CSS code in terms of code distance or this kind of like logical dimension. So it can be something very trivial. For example, the surface lattice surgery, there are only 2, or if you have distance d, then d minus 1 physical qubits align on a line. Yes, so what matters really much is how you connect these 2 systems. The connection map. So you want this connection map to commute, then meaning that you will need an extra condition that so it is this direction equals to this direction. Yes, and after you have this valid mapping, a valid commuting diagram, then what you get is a so-called merged code. So what you do is that we simply take the direct sum of the different modules, R modules or vector spaces. Then we are able to define 2 parity-check matrices as if they are like CSS code. They are CSS code, just like we are able to decompose them into the original part of the data patch and the part which corresponds to the auxiliary qubits. Yeah, so as you know, like the columns of the parity-check matrix representing the qubits. So the first half representing the data qubits. So it's this vector space, and the second half representing the auxiliary qubits, which are this U0. And in terms of lattice surgery, it's just a middle extra physical qubits. Yes. So what is the measurement doing? The measurement is simply, so here we are representing like displaying the Z type of measurements. The previous one is the X type measurements, but it's just like a like the inverse process, but not an inverse, but a dual process, but that'll be very symmetric. So what we are measuring here is the stabilizer of this merge code this whole thing, this whole system, and these extra rows which are introduced by the connection map and the original, the checks of the auxiliary system. And as you see that there's a intersection between the data physical qubits and these extra rows. So the measurement on the logical operators or the PPM that we want to realize are located at this intersection regime, or are realized by product of rows of F1 star. And in a ideal case, or most of the valid case, when you get some product of, or if they're on binary, then sum of row F1 star equals to support of your PPM. So let's say this row is a specific subset, and then simultaneously the sum of the specific subset of rows on partial 1 star equals to 0. Meaning that when you get the measurement of your PPM, you don't measure out anything like the extra on the auxiliary system. So that is exactly what happens when you do the lattice surgery. The middle ones get canceled out. The middle ones, yes. So, okay. So one more thing is that the number of PPMs are being executed are calculated as follows. Yeah, so here B is simply for the binary representation, because like we ultimately want binary ones. And yeah, so it's not something quite difficult. So it is just like, say, simply a readout from this structure. And the reason that why we care about this number is because in lattice surgery, it is straightforward that we only have one measurement. But when you come to high rate LDPC codes, we consider this kind of like parallelism. That's what we want. We want to measure more than one PPM at one time. Okay, so we just introduced this kind of like very general framework, and we all again add some constraints on this kind of framework. So first of all, we choose our candidate, the data code, to be a CC code. That's fair. And we pick the auxiliary system to be exactly the same code. So it's another copy of the same code. That's a very special constraint. And we also want to, yes, we want to point out this product construction, this product surgery works in general for all the product constructed code, but for simplicity, we just emphasize on CC code. And simultaneously, we want the connection maps, so these ones, to be also the parity check matrix of a lifted particles with extra constraints on the seed matrices. They need to be in some sense binary. So HA prime and HB prime only can take like 1 0 0 0 0 0 0 0 0, something like this. But this is not a binary matrix in real sense, because this one is defined over the ring. So if you consider its binary representation, it still leads to an identity map, something like this. Yes, but these are the constraints. And the reason that we want these constraints are less straightforward. So we want, it's very, like, say, mixed with the structure of the logical operator basis, but it can be illustrated with an example later on. And yes, and for commuting reasons, that we want HA and HB to be in the same shape of the seed codes that we choose for the data patch. Yes, and yes, due to the time limitation, I don't want to expand how this kind of like results, how many numbers of measurements that we can do is derived. But again, you can see from, okay, I think I have a tiny one. Yes. Okay, so we skip the derivation and we just emphasize on this rank. So we know after a bunch of derivation, if you believe me, that the number of measurements that are being performed is the rank of this HZ prime. So which is this one. If you still remember, the measurements that we are really doing, that we are really concerning, is these two parity-check matrices, and this one is what really behaves on the data code patch. So the rank of this matrix determines like how many logicals that we can measure, or how many ppm that we can measure. And this matrix is of size this one, like NAMB times 2 NAMB, which is fairly easy in terms of it is a lifted product code. So if you still remember, HA times identity tensor HB, something like this. Oh, so well, this is HX prime, but HZ prime equals to identity tensor HB prime. Yeah, something like this. But and this identity has some sizes, and so you can verify yourself it is of this size. And if you consider its rank, you can never get more than NA times MB, which is half of your logical qubits, because like they are in the same size of the seed codes, and we have K equals to 2 NAMB. N equals to 2P NAMB. So these are the code parameters. Yes. So that's exactly upper bounded by half of logical qubits. So if you, and that directly comes to the question, okay, so if we consider two products as a pair and they are disjoint, then can we really achieve this upper bound K over 2 pairs of measurements? The answer is yes. For arbitrary CC codes, that there exist configurations of ppms such that this maximally parallelism is achieved. And we show with a tiny example. So we consider these two CC codes, the CC code of a 24H3 code with the parameter 3, and in ring sense, it's just like this. And with these are the parity-check matrices. And with the product construction, we get their parity-check matrices over the ring level. And we can derive their logical operator basis based on the Kunis formula, and on a Tanner graph on a ring level, they're just simply represented by 8 dots, 8 circles separated into 2 clusters. Okay, so the goal is to achieve K over 2, which equals to 4 pairs of ppms in parallel. And with a fixed overhead, which is straightforward, as we are fixing the auxiliary system to be another copy. And so a very straightforward illustration is that, okay, can we do, so because like, okay, let's do this. So for example, like we have the first one here and the first one in the other sector. Can we just measure these two and these two? And so just like the corresponding one, we want to measure their joint product. And so how we do this? It is quite straightforward. Yes, by restricting how we choose this HZ prime, as this HZ prime is which we actually act on the data patch and determines like which ones we want to measure. So how do we choose this HZ prime? We choose it such that there are ones on each single position. So like for the first measurement, it is 1 on the first 6 position. On the second measurement, it is 1 on the second position on both sectors. So this is sector 1, this is sector 2. And so this is simply achieved by you choosing HA prime and HB prime to be identity matrix. So identity tensor identity, you get a identity of size 4, and 2 identity of size 4, you get this HZ prime. So in such a sense, we are able to realize that if we want to measure the joint product ppm of 2 logical Z operator of the same position in 2 sectors, we get what we do is that we simply take the corresponding row. For example, we consider this 2, the second one, which is this one and this one. If we want to measure their joint Pauli, we just take this second row and we multiply it by chi. This chi multiplication on algebraic point of view is just like multiplication, but on a physical level, what you do is you simply do, after you take the binary representation of this ones, you just get an identity matrix and you sum all the rings, all the rows of this identity matrix, and you get a matrix full of, a row full of ones. So that is corresponding to a logic operator. And so after you multiply this chi, and you see the first half becomes chi, like 2 chi's in different positions, and the remaining part, as they are all binomials, they are cancelled by a chi multiplication. So at the end of the day, we are happily achieved this support of 2 logical operators, so 2 single chi logical operator, and they are measured out within this single round, and the other ones can be achieved just different choices of rows. Okay, so a short comparison, and then we may end up this one. So a maximal parallel surgery for the CC codes compared with other protocols. So here we mainly compare the works that done by IBM. I think both are from IBM, yes. So when the maximum parallelism is available, we are always able to reduce the time overhead by a factor of k over 2, because that we are able to perform k over 2 logical measurements. The space overhead is always the same, because that we are taking another copy of physical qubits, and if you remember, we are having k n nkd as code parameter. In that sense, this n is only about data physical qubits, so we need extra n for check qubits. So that's why a extra copy is actually 2n of space overhead. So space overhead is relatively high compared with other methods, but as we have this kind of like parallelism, which realizes a factor reduction, and it turns out the space overhead at the very end, in like say in total, is comparable or even better, or like say way better than the state-of-the-art protocols if you do them like say in like one by one. And yeah, so here we assume that n almost equals to k times d, which is true for all the codes that we have presented for small sizes. Well, not small sizes, but relatively not large sizes. Yes, for less than 200 physical qubits. Yes, for all the comparison here, we only consider the single merge, which is either a single logical measurement or a joint logical measurement of 2 same type logical operators. So the single measurement is just like measuring out the logical qubit itself, and the joint measurement of 2 is just what we have shown previously. And yes, so with a solid example that we compare with the what IBM done with the extractor method for this gross code. What they can do is that, when we achieve this maximal parallelization, the space-time overhead for our code is reduced by like around 300 physical, 300. There's no unit, but 300 space-time. And one thing worth noting is the time overhead, because like it is highly related to the distance. So they start with 12, which is the same distance as they do, and we start with actually 14. So it is 14 divided by 4. So yeah, but they are still like fair comparison. Okay, so yes, just one more sentence that there are some limitations of product surgery in hybrid in this product measurements, because like of this product construction of the connection maps. So for example, if we look at this logical qubits, we are only able to measure the joint Pauli between the, like say, lightly colored, lightly pinked one. So we can do this two, okay. So this two, that's fine, or this two, they're all good, but not with the green ones. But if you remember that we have some logical swaps, such that we may able to generate like all ones for all the CC codes, or all possible combinations with all CC codes, but that hasn't been shown for all CC codes. What we have shown is that it is possible to do so for the 2483 code. And yes, so what we also mentioned is that we introduced this hybrid gadget, which is okay, if you have some cases that you can't do, for example, like you want to measure these two, the joint Pauli of these two, you can't do them simultaneously with the product surgery, then you just do it with the one of the state-of-the-art measurements scheme. Then you just boost your measurements with this product surgery whenever it is possible. And this is a reduction of space-time overhead. And you can see, so it's still like we only consider single logical or joint of pair of two. And so when it is mixed, so all possible cases are being considered, there's a almost like 140 overhead, space overhead reduction. So, and we are considering this 136 physical like qubits code, then it is almost like a n reduction. So it is quite good in terms of like space overhead. Okay, so this is my, almost the last slide. Yes, so how we realize this logical Clifford over 4 logical qubits is that and we are treating the other 4 logical qubits as auxiliaries, is that we have this new decomposition of Clifford groups. Yes, so the Paulis, the single logical Paulis are easy, as you can see, like they are fairly addressable. And the CNOTs, arbitrary CNOTs, are realized via the parallel surgery, as just mentioned. And arbitrary CNOTs between these 4 logical qubits can be, like they addressed in parallel, or like they just they're on their own, but they can also be done in parallel, and arbitrary combinations of disjoint CNOTs. And also SI Steiger. So 2 S gates. So if you remember the the CZ gates, that we have CZ between these two, CZ between these two, and S dagger. And if we treat, for example, like these ones as auxiliaries, then we are able to realize S and S dagger on 2 logical qubits. And we show that with parallel surgery and logical swaps, we are able to realize I and j to be arbitrary combination of 4 logical qubits. And yes, so this global hardmode is just like a hardmode swap, and with logical swaps such that you can get rid of this swap. Yes, okay, finally. Discussion and outlook. So this is at least to my aware, the first logical code design. So we designed this code and in parallel as a twin. It's a way to do logical operations. So such that we realized with this like good addressability and also of course good parameters and a parallel logical PPM, which can be used for other product codes and with a fixed space overhead. And they all together becomes this maximum parallelism that we just introduced. So this K over 2. And it is also very interesting that like say this work is purely on lifted product codes, which you will see, you see, and the tenor graphs are now listed in the maybe the way that most people are familiar, that on a surface code level, and because like there are almost like say all connections are long range connectivity, but that is not a problem for the neutral atom platforms. And in fact, there are many papers shows that lifted product codes and hypergraph codes, those codes can be realized on a neutral atom platform with a very high parallelism. But I don't expand on that point, but this work is really hardware, or at least neutral atom hardware friendly. And yes, so above are some outlooks. Below are some outlooks. So the fault tolerance of this product surgery is something actually slightly open. So what we have shown is that it is fault tolerant for all the HGP codes, hypergraph protocols, and we numerically verified all presented CC codes and all possible combinations of surgery that you do. They are all fault tolerant, but we haven't shown it is fault tolerant in general for all possible product codes, lifted product codes, and the others. But I do feel like very confidently it might be the case. And other structures of logical operator basis are, and like say of the high-rate LDPC codes and co-design computational gadgets are really, I mean, like say welcome. Like there must be some. I feel like this kind of co-design idea is the right way to do, and we just need to find a better trains which can really be used for scale later on, like the better scalable and better efficient computation. Also, like we realized that there's some fast surgery process which realized to reduce the D rounds of stabilizer measurement to a constant. And such are realized in sometimes by the single shot decoding property of the codes. And there might be something we can do similarly at a small space overhead. And we enable the parallel as well. And yeah, so as mentioned, that this kind of like new generating set of the Clifford groups makes the compilation of the Clifford group extremely easy for this specific CC code. So there might be some other generating sets of Clifford groups which are not usual, but also quite helpful for the research. So it is very something worth looking at. And yeah, that's pretty much the end of my talk. Sorry, I'm a bit running late, but okay.
All right. Right. Yeah, I think, yeah, it's fine. Yeah, thank you very much for this very informative talk. Yeah, I guess we're running over the time, so maybe like one quick question or comment if anyone in the audience has one. I don't know. Actually, for me, I just have a question of like, is I guess like, so you were talking about, so this is not really going something that you would want to do asymptotically, right? But in some sense that doesn't matter, right? Because anyway, I want to, if I'm going to implement this on some really large scale quantum computer, what are we looking at? Like maybe size of, okay, what's the size that they usually say? Is it like 1,000,000 qubits? Maybe.
So for example, like the recent Caltech paper, they initialized this new company. They said the RSA can be done in 10,000.
Oh, 10,000. Okay.
Yeah,
Okay.
but with 170 years. Yeah, but so I would say
okay.
this one too, and so 100,000 and with like 90 days. So I would say like any regime between this would be something worth looking at.
Okay. Okay.
Yeah,
But
10 to
I guess like my question is sort of like, so at least you foresee that this method that you have will still be like performing well in this kind of range, right, Reggie? Or
yes. So the codes that they're considering in this work is also a LDPC code, and but with a slightly larger size, like around less than 1,000 physical qubits. So I would say some codes between some code like itself is less than 1,000 physical qubits. Will be some like honey point, sweet point for both, I don't know, logical operation and good finite size case. Because like there's an observation that those good asymptotic code, they might don't have good finite cases, at least for hundreds of physical qubits. At least like people didn't find any yet. So this might be a trade-off.
Okay. So anyone with a question or comment? Okay.
Yeah. Hi.
Oh,
yeah,
hi.
I just take a call and get back. So because I was doing quantum simulations and I saw you can do the XX and ZZ. I guess it's logical XX ZZ operations. Yeah. So do you think like if we want to do like more K-local like XXX, XZZ, like familiar in quantum simulation, will this design benefit that type of operation, or you still need to decompose like XXX gate into like basic XX gate plus some T gate? Like you think there is a benefit from your code?
I kind of get what you mean. So you're asking, so for example, can we measure XXX of this three?
Yeah, your measure will create the logical XXX. Is it correct? Or I think like your measure of I saw your measure of XX is to do the CNOT, right? To create a logical CNOT or create some logical.
Yes, but I mean, okay. So you're saying like if we measure this like multi-qubit joint, will that benefit to creating logical operations?
Yeah, in more qubit.
Yeah. I would say yes, but I'm not quite familiar with that. But if you consider, for example, if you want a Toffoli gate, so some like say multi-qubit Clifford, then you definitely want a multi-qubit measurement, and this kind of like addressability, which is like the cluster logical operator basis, then can also benefit from it, like in terms of doing so. And actually, like we can do this, for example, like this 3 logical measurements. Yes. But yes.
Sorry. Yeah, because I was thinking of your code design. I think is really good. So, like we are also working on the like code design of error correction and fermionic to qubit encoding. So it's like a code design of this fermionic error correction code. And I think maybe this will be helpful in this region. Yeah.
Yes. If your target is to measure the, like say, joint logical, and you want them to be like say addressable like this, then I would say this one is definitely a good choice to try at least.
Yeah, because I was working on the BB code now, but since in your result you showing you are better than BB code in almost any
No,
perspective.
we're not saying we're better than BB code in almost anyone. I mean, for example, like in the hardware side, BB codes are designed almost for the superconducting platform. So the connectivity is a big issue, but our code don't have nearest neighbor connection. So it is almost impossible to realize on a superconducting platform. So BB codes, they have great advantages, and they are studied a lot. But I just feel like leaf codes, which needs more investigation. Maybe not this CC code, but in general, this leaf codes, they have very good advantage, like a potential at least. And also, like for example, mentioned in this recent RSA 2048 work by Caltech, they are using leaf code as well. So it is something really worth looking into for the community, I feel. Yes, and also like the CC code is good.
Yeah, because normally we are shifting to neutral atom, so I think CC codes will better fit in that region. So
yes, if you are considering neutral atom, I would say definitely.
Yeah. Okay, really good talk. Thank you. Yeah.
Thank you very much.
Right.